Okay guys, so welcome back again to another video. If you remember our previous video, we have started talking about the thermodynamics and we have talked about the first law of thermodynamics. So we are going to move more deep into this first law of thermodynamics. If you remember, this was our equation which we have obtained from our first law. The internal energy difference is equal to applied heat plus work. So this work, this is much important and this is much complicated, right? So in this video we're going to talk more about this work. I have told you in our previous video this W represented the work done on the system. This is important, done on the system. If the system is the one who's doing the work, right? If system is the one who's doing the work, then W becomes negative. If the surroundings doing the work on the system, then this work becomes positive. In our previous video we have introduced to this piston system, like here there's a compartment, we have a gas and we have put a piston on this gas. So this is our system now, this is our surrounding. Now let's talk about this work, especially the expansion work. Okay, expansion work. Let's say we have a external pressure. Here we have the external pressure of p.w.atkins. This is a piston. Assume this piston is weightless, frictionless, so massless, so no force applied from this piston. Now what I'm going to do is I'm going to apply a force. I'm going to apply a force in up direction. Here you have the F, and move this piston like this position. Okay, let's say the difference, okay, the difference of this distance as dz. Okay, this difference is dz. So you know this is a distance, right? So this is a distance, this has a direction, so this is its direction. Now you can tell me whether the system has done the work or the surrounding has done the work. You can see system is the one who's pushing this piston away, right? System pushing this piston away, which means the system is the one who's doing the work. The system is the one who's doing the work. Now, if you remember your basic physics knowledge, there's an object, we have applied a F force and we have moved it on d distance. If I ask you to calculate the work, how can you do it? You will just do a simple calculation. Work equals force over the distance. So same theory applies in our this situation too. So let me erase this. Okay. Now what happens is we need the work, right? We need the work which has done from the system. So how can we calculate the work? So here I will write it as dw, because the change of work, right? The change of work, I can write it as F, the force, and d is it, the distance. Now if you remember, you can see here I have written a positive value. Here I have written a positive value, but we have introduced this term the work, and in a previous video I have explained why this work, okay, this work done by the system should be negative. Here also the work is done by the system. System is the one who's pushing the piston away, so system has done the work, which means this work has to be negative. So we need to apply a negative term in order to satisfy that condition. Sometimes you may see, especially in physics, this minus term is not there, like this W is negative. Likewise in big, it's because physics is talking all about the surrounding, right? Physics is all about talking the surrounding. So like in physics, this is not happen often. Like in some textbooks you may see this W term is introduced as work done on the surrounding. So you can understand the signs are changing. For now we are in the chemistry, so I'm just gonna stick with our original definition. Okay, this is work done on the system. So work done on the system is positive, work done by the system is negative. So in this case, you can see the work is done by the system. So your work has to be negative. So this is the work. To satisfy the basic condition, I have put a negative sign. So this is our dw. Now to this scenario, I can apply our first law of thermodynamics, which is du equals dq plus dw, right? So let's assume there's no heat change, right? So which means this dq is 0 and this du equals dw. So we are going to talk lot about the work. So we are going to focus about the work. So let's just take this work term. Let's take this dw term. Okay, how we can write this dw term? This is the work. This is the work. So basically, just like here, just like here, I'm going to write negative f d z. This is our work. Now let's see here. You know what's the equation for the pressure, I guess. We can write an equation like this. Pressure is equal F over A. So let's assume this area of the piston as A. Now I can derive an equation for this force, right? P times A equals force. Here I'm going to substitute for this force. dw equals negative. For force, I'm going to apply these two terms. P, the pressure is PEXT, right? Pressure is PEXT. A means the area and D is it. Okay. Now look at these two terms. A and D is it here. This is the A, this is the D is it. This is a cylindrical shape, so which means A into D is it basically gives you the volume, right? The volume change. This system has initial volume and now at final system has this kind of volume. So this A times dz gives you the change of volume. So I can substitute for these two terms dv, the change of volume. So now I can write my final equation as PEXT dw. So these are derivative. If you know, like if I want to calculate the total work done, right? If I want to calculate the total work done, what do I have to do? Here you have the total work. I just need to integrate this. V initial and V final. PEXT dV. So this is my equation, right? So in special condition, like let's say PEXT is constant. Assume it, okay? Because there can be some system like some scenarios where the external pressure is changing, right? There can be such scenarios, but there can also be scenarios where the PXT or the external pressure is constant. Next example is let's say you have an open compartment and there's a reaction is going on, let's say A to B, and this B is the gas. So when the reaction is going on, the B gas is forming, okay? So when the gas is forming, you know pressure is going to be increased, but this is a open compartment, so the surroundings pressure is the atmospheric pressure. So this pressure is a constant, right? This pressure is a constant. So this case, in this open system like this case, you have a constant pressure, but there can be pressure changing scenarios too. Let's assume we have PEXT as a constant. Now what happens? A constant can be taken out from the integration. So we have the W negative PEXT VI VF dV. So I hope you know how to do the derivation, right? Sorry, not the derivation, integration. There's simply one here. there's simply 1 here, so you can write the derivation as v. So you have the limits vi and vf. So with the limits applied, you can write the final equation as p.ext vf minus vi. So this is our final equation, right? This is our final equation. So that scenario, like the works positive or negative thing, right? We can explain it by here. Look at this. Let's say the first scenario, the system is the one who's doing the work. System is the one who's doing the work. Now what happens? You can see this system pushing the piston away, which caused to increase of the volume. So now you can see vf means the volume of the final state is bigger than the v initial. So when you apply that condition here, you can see this is positive. When this becomes positive, the whole component here, whole term here becomes negative because there's a negative sign, which satisfy our basic condition, right? Work is now negative. It's correct because the system is the one who's doing the work. System gives away its energy, so work has to be negative. System is the one who's doing the work. In the other case, let's say the other way around. Our surrounding is giving a force and compress our gas. So basically the piston is coming down. Now what happens? Surrounding is going to do work on the system, this case, which means work has to be positive. Now let's say here, now when this happen, you can see now the piston is like in this form. V final is lower than the V initial. V initial was here, V final was here. So in this scenario, you can, if you apply it that case, you can see this is smaller and this is larger. This becomes negative. When this becomes negative, you can see negative and negative becomes positive. Now our work is positive. It's correct, right? Because now the surrounding is the one who's doing the work. Surrounding is doing the work on the system, which work should be positive. This is very fun, and this is very how can we put it, like it flows very perfectly. I hope you can understand this concept. This is very much easy, right? This is not that much hard. Just understand the basic concept, what is the work and how this affects the system and surroundings. That's the main thing which you need to be aware of. And then let's move a little bit forward about the reversible expansion. Okay, now let me take that our procedure again. Here we have the compartment gas, and here you have the system. Sorry, here you have the piston. System is here. System is a gas, right? This is a gas. So here you have a PEXT. And let's say our internal pressure is PI. Now this reversible expansion means, okay, your piston is, your system is at a mechanical equilibrium. Right? Mechanical equilibrium. This is equilibrium, right? A small change in PEXT or small change in either of these two pressures, you can change the direction of this workflow. You can either do the work on this way or this way. A very tiny change, you do tiny change in either here or here. You can change the direction of this work, whether you can do the work by the system or on the system from a tiny change from either of these two pressures. That's basically the mechanical equilibrium, right? That's basically the mechanical equilibrium. So in this case, when this at the equilibrium, we say PEXT is equal to PI. Our external pressure is equal to our internal pressure. Otherwise, it won't be an equilibrium, right? Let's say like our PEXT is considerably larger than the PI, then you cannot reverse it, right? No matter what we do, if this is larger, then this will push down. We cannot reverse it. If this is equal, we can do a tiny change for either of this term to reverse the action on this piston. That's the concept. So this is a mechanical equilibrium. Now let's take the work which we have derived before. Basically is that this one, Vi, Vf, negative, Pext, dV. This was our equation which we have derived before. Now you can see our Pext is equal to Pi. So now I'm going to apply the Pi into this equation, negative Vi and Vf, Pi means the internal pressure, and dV. Now you know this Pi means the internal pressure, internal system is a gas. So let's assume our gas is an ideal gas. Right? Let's assume this gas is an ideal gas. In ideal gas, we have an equation PV equals nRT. So now you can take new terms, or you can write this your pressure in terms of V. Here you can write the P equals nRT over V. So I will write it over here. Now I'm going to apply this P. I'm going to substitute this P with the nRT over V, negative Vi, Vf, nRT over V dV. Right? Now you can see this n is a constant. Our system doesn't change the moles in here. Let's assume that. And R is always a constant. It's a gas constant. V can be changed. V is the variable, and T, our temperature, is a variable. If we look at the isothermal system, or that T is a constant in this case, right? We can take out these whole three terms out from our integral like this: nRT, Vi, Vf, and we have dV over V. If you remember these integrals, right? I'm not going to talk much about the integrals. Just know when you integrate this, you will have your equation like this: nRT ln Vf over Vi. This is our final equation for the reversible case. Okay, this is the reversible expansion. So you need to identify the system and scenarios, right? If it's a reversible expansion, you need to go through this one. If it's a constant pressure, right? If it's a constant pressure situation, then you can directly apply for this equation. Okay, so this is basically the equation. And the same conditions apply here too, right? Let's say the system is the one who's doing the work. If the system is doing work, you know the W has to be negative. So this is the W equation, right? This is the equation for the W. And let's say system is doing the work, so which means the piston is going upward. So Vf is larger than the Vi. So in this case, Vf is larger than the Vi, so which means the ln is positive. When ln becomes positive, this whole component becomes negative because there's a negative sign here, which means W is a negative. It's acceptable. Other case, let's say our surrounding is the one who's doing work on the system. Then what happens? Our system's work has to be positive. When the piston going downwards, you know Vf is lower than the V initial, right? When you apply that terms over here, this is smaller and this is larger. Ln term becomes negative, right? Ln terms become negative. If I want to explain it further, like let's say here you have ln 10 to the minus 3 over 10 to the minus 10. Sorry, 10 to the minus 1. Now you can see whole answer is 10 to the minus 2. So you can take it out for negative 2. The ln term is negative like this. So when this becomes smaller and this becomes larger, right? This becomes larger. This whole term becomes negative. So negative becomes positive. Your work is positive. Acceptable, right? This is the basic terms you need to understand. So these are the basics in our thermodynamics. So I hope you got the idea about this work. This is very important. The work is very important when it comes to thermodynamics. I hope you understand the mechanisms of it. So in our next video, we will do some quick examples and questions to practice this up.